Okay, so this is joint work with my former postdoc, former postdocs, Evgeny Lucaro and Christopher Wahlén, and my current PhD student, Douglas Svensson-Seth. Okay, so I think most of you have seen this picture, but I wanted to start basic because, yeah, I mean, I've seen that there are talks on several different topics. So, I mean, this is the picture we've all seen of two-dimensional water waves, and then three-dimensional water waves might look like this. So doubly periodic in two different directions. And well, I mean, the patterns can look a bit different. So they can appear in the lab, but also in nature. So I'll be talking about these types of waves, and it's good. I mean, it's I think very suitable for this workshop since it's something that Walter Gregg worked on. Okay, so I'll go through this rather quickly then. We consider, well, okay, so the assumptions are that the water is inviscid and incompressible, but not irrotational compared to the last talk. And we'll be including surface tension, but no ice sheet. Okay, so these are the Euler equations we all know. And I will be including surface tension. So maybe I just note that I'll use this MathCal H for mean curvature essentially. So when I don't want to write out all this stuff, I'll write it like that. Okay, so we'll be looking for steady or traveling waves, traveling at some speed c in, well, let's say in the x direction. Later on, it will be, well, okay, kind of variable, but all of this is to say that when we're in a moving frame, we get this steady problem instead. Okay, so we consider this in the unknown domain omega eta, bounded about by the free surface eta. And we assume that is a graph. Okay, so, right, so now I wanted to give some background on just looking at the steady and compressible Euler equations in 3 dimensions. So without assuming anything about irrotationality. So then in 3 dimensions, the vorticity is a vector, the curl of the velocity field. And okay, so 2 important equations are the vorticity equation, which looks like this in 3 dimensions. And another equation which would be important is what I call Bernoulli's equation in 3 dimensions. So it looks like this, where h is the Bernoulli function. So basically this equation, well, I mean, you can interpret this in different ways, but it tells you that surfaces of constant h, so Bernoulli surfaces, they are tangent both to the velocity field and to the vorticity. So this is important later on. And essentially, well, either of these 2 are equivalent to the Euler equations. So looking at this, so how you would interpret Bernoulli's equation is saying that u cross omega should be the gradient of some function. And if that is true, then you can define the pressure so that this identity holds. Okay, so I need to say something about the structure of these equations, or Arnold's structure theorem. So this is a little bit complicated to take in all of it if you haven't seen it before. But so essentially, this is a dichotomy between 2 different types of solutions to the steady Euler equations. So consider the steady Euler equations in a bounded domain, and assume that, well, so the flow is tangent to the boundary. And also for, well, so in Arnold's statement, everything was assumed to be analytic. This is not entirely necessary. I mean, then you get a slightly different version. So the first case is if u and omega are not everywhere collinear, then essentially omega is divided into different subdomains. And in each subdomain, well, so each subdomain is either fibered by invariant tori, and on which the flow is conjugate to a linear flow, so either rational or irrational. Or each subdomain is fibered by invariant cylinders, which have their boundaries on on the boundary of omega. And in that case, the flow is periodic on each of these invariant cylinders. So that's the integrable case. And these invariant tori or cylinders are the level sets of H. So the other case is if U and omega are not are collinear. So that's the chaotic case. So these are the Beltrami flows. And well, in that case, it's known that the streamlines can be dense in an open subset of R3. So the classical example being ABC flows. And there is also a very interesting recent preprint by the Spanish group where they prove that sort of chaotic behavior is generically true for Beltrami flows. Okay, so this means that there is a very special structure of solutions to the steady Euler equations. Well, so let's recall how what happens in the two-dimensional setting. So that there things are sort of more, you can't take this structure for granted. So in 2 dimensions, assuming that one of the horizontal components is 0, so then the vorticity is just, all but one components are 0, and so we just have the scalar vorticity. And then the vorticity equation simplifies to saying that omega, the vorticity is constant along the streamlines. And if you combine that with U being divergence free, then you can write U as, so U is then, the sort of perpendicular gradient of a stream function. And the stream function also has to be constant on the streamlines, sort of by definition. So therefore, there is a functional relationship between the two, except for in degenerate cases. And then you can reduce everything to this nice semi-linear elliptic equation. And okay, so that's sort of looking at the vorticity equation. You can also write down what the corresponding version of Bernoulli's equation is. So just sort of simplifies to this relationship between the Bernoulli function and the vorticity, the stream function. Okay, so some example of important flows in 2 dimensions are shear flows, So the simplest one being so this kind of explains what this vorticity function gamma does. So in the simplest case, it's identically 0. That means that we have irrotational flow, and then the current is just uniform. So the next simplest case is if you take constant vorticity, in which case you get the linear shear flow. And for a general vorticity function, you can get something looking, essentially what you like. Okay, so this slide is just to say that there has been a lot of work on the 2-dimensional case. I'm not going to go through all of these examples, but we all know that there's been a lot of work on the irrotational case going back to Stokes. And the rotational case is both older and newer, in the sense that there was an explicit solution by Gerstner before Stokes' work in Lagrangian coordinates. But then there has been a recent line of work, starting with Konstantin and Strauss, constructing large amplitude solutions for general vorticity functions. And then there's been work by many people, including some who are in the audience. Okay, so in 3 dimensions, there's considerably less work. And I mean, one of the main reasons being that, there is no reduction in general to an elliptic free boundary problem. Okay, but there has been work on the irrotational case. So let me say something about that. So, okay, so here's the vorticity equation again. And one solution to this equation is, of course, to take omega identically equal to 0. Then this is trivially satisfied. So that means that the Bernoulli function is actually constant everywhere in the fluid. And so, I mean, you can define the pressure essentially like this. So work on three-dimensional doubly periodic water waves goes back essentially to this. Well, I mean, I think there was previous work on the linear problem and so on, but rigorous work on the nonlinear problem goes back to Reeder and Schimbrodt around, well, in 81. So they considered the case of symmetric diamond waves. I'll maybe say a little bit more about that, the symmetry assumptions later on. And then, so important and a very important result was the one by Walter Craig and David Nichols, where they considered a more general case where you allow, so essentially doubly periodic means periodic in two different directions. And so you have a sort of fundamental domain which defines the periodicity. And Craig and Nichols considered the case where this fundamental domain is arbitrary. So they used, well, okay, so they used the famous Craig, Sulam, Sakharov formulation and variation of Lyapunov-Schmidt reduction to construct waves in that case. So there is a difference sort of between these two. Reeder and Schimbrodt is simpler because then you can use the standard bifurcation from a simple eigenvalue approach. Whereas in the asymmetric case, the kernel is at least two-dimensional. And well, Craig and Nichols also considered the case where you have higher dimensional kernels. Okay, and then there's been several other works, including work using spatial dynamics by Groves and Mielke. Well, it started with this paper, and then there are several versions of this. And yeah, so this is all when you include surface tension. Yeah, okay, so that's something I forgot to mention before. So there's an important distinction here between the two-dimensional case and the three-dimensional case. In two dimensions, there is a lot of work. Well, I mean, actually, it's somehow, in some sense, it's easier without surface tension, in the sense that then you can use maximum principle type arguments. Whereas in three dimensions, it's actually much easier to work with surface tension. So without surface tension, you run into small divisor problems. Nevertheless, there is this very fundamental work by Jos and Plotnikov proving the existence of doubly periodic pure gravity waves. So the first paper was on the symmetric case, and then the second one for asymmetric waves. And both of them use Nash-Moser theory. Okay, so now let me add vorticity to the equation. So the first result, I will talk about two different results. The first one has appeared recently in ARMA, and the second one is work in progress. So in the first case, I will be considering, well, I already mentioned Beltrami flows. So this is a special situation when things simplify a lot. So, well, okay, so here's the vorticity equation again, and I already pointed out that a special solution is omega identically equal to 0. So another solution is to take omega, a constant multiple of u. If you plug that into this equation, you see that both sides are identical. Okay, so another way to look at it is through the Bernoulli equation. Remember that u cross omega should be the gradient of some function, and that is trivially satisfied if they are collinear. So then again, just like in the irrotational case, the Bernoulli function is constant. And so the pressure is given by this expression. Okay, so that means that we can consider waves on Beltrami flows, and the equations simplify a lot so you get these equations. So instead of considering the full order equations, we just consider this equation. So the curl, remember this is the vorticity, the curl of the velocity field. This should be a constant times the velocity field. And the other things, right, okay, so these conditions are the same as before, and this is then similar to the irrotational case. So instead of the dynamic boundary condition saying that the jump in pressure from the air into the water is proportional to the mean curvature, we can use the Bernoulli, simplified Bernoulli equation to substitute in this expression. Okay, so these are the equations which we consider, and it includes as a special case the irrotational waves. So if you take alpha equal to 0. And maybe I should point out that there's a technical issue here. So I said that these are Beltrami flows. So these are sometimes called strong Beltrami flows when this constant here in front of the U is actually a constant. So you can also allow it to depend upon the spatial coordinates, but that's much more difficult because then you actually get an equation which this has to satisfy in order to get for the U to be divergence free. Okay, so right, so I said that in general the 3D equations don't simplify to an elliptic equation, except in the irrotational case. So that's not completely true because this is also a case where you get an elliptic problem. But now it's a system rather than a scalar equation. So you can think of this as a sort of div curl problem. Okay, so to get some sort of intuition, we look for some special type of solutions. So remember in a 2D case, we had these different types of shear flows, which we can use to bifurcate from. So what are the corresponding solutions for Beltrami flows? Well, it turns out that there are also a type of shear flows, but where the direction depends on the vertical level. So the flow in each layer is uniform, but then the direction changes with height. Okay, so you can get this sort of two parameter family of trivial solutions with C1 and C2. So I sort of think of them as the velocity field or the velocity parameters. So I will use both of them as bifurcation parameters. Okay, so now, right, so I've now modified the equations a little bit. So what I've done is to add an integral condition, which we need for uniqueness purposes later on. So it's the same equations as before, but then I've added two integral conditions. And in addition, I've changed, well, so I've fixed the definition of the Bernoulli constant Q so that it matches the Bernoulli constant for those solutions I showed in the previous slide. Okay, so this is the specific problem that we will look at. And in addition, we need to specify the periodicity conditions. So we assume that the surface and the velocity field, are both periodic with respect to some lattice. So the vectors lambda1 and lambda2 generate the periodic lattice capital lambda. And omega, 0, 0 is the fundamental domain. So sort of one domain which is then periodically copied throughout the lattice. Okay, so this feature is already up here. I mean, the integral should be over one cell in the lattice. Okay, so in addition to this, we also assume some symmetry conditions. And this is slightly different compared to the irrotational problem. So it turns out that, so in the irrotational case, you have two reflection symmetries. And here there is only one. So we can assume symmetry with respect to reflection in the origin of the plane. So this is what we do here. Well, okay, so you have that symmetry for eta, and for the velocity field, it's slightly different. So you have the symmetry for the horizontal variables, and for the vertical, there is a minus sign. So we use these symmetries to reduce the dimension of the kernel. In the irrotational case, as I said, there is an additional symmetry, which you can use to reduce the dimension of the kernel even further. And that's what Reader and Schimbrot used. So you can get bifurcation from one-dimensional kernel, and that's not possible here. Okay, yeah, so there you have the symmetry. Yeah. Okay, so now what we do is we follow the classical approach and linearize around one of these trivial solutions I showed you before. And then you get a bifurcation equation or a dispersion relation. So if you have worked on the irrotational problem, then you will recognize a lot of this. So what's different is these alpha terms here. The function kappa is defined like this. So in the irrotational case, you take alpha equal to 0. Well, so then we only have this third option here. And so then this disappears and this disappears, and you just get this hyperbolic cotangent function. And then you see that it's exactly the same as in the irrotational case. So what happens when you add alpha is that so you get this additional term, and then in addition you have this this thing here, and then there's an additional periodic behavior if alpha is large compared to k. Okay, so I'll say something about the main result. So we fix alpha, it's arbitrary, so it could be 0 actually, sigma and d, as well as the laminar flow. And we get lambda prime with a dual lattice. And then we need to make certain assumptions which we can verify in special cases. So essentially what we need is that the dispersion relation, which I showed you on the previous slide, has exactly 4 roots. So now for fixed C, I think of this as an equation for the wave vectors generating the lattice. So K1 and K2. Okay, so these generate the dual lattice, sorry. Okay, then we also need some other technical conditions. So maybe I'll skip the details here. And we need a certain transversality condition. Under these assumptions, there is a 2-parameter family of doubly periodic solutions close to this laminar flow which we bifurcate from. Okay, so let me give you a brief outline of the proof. So the idea is to make a reduction to the boundary, so similar to what has been done in the rotational setting. So we do that by, we do that by solving first these equations for U and then plugging them into the Bernoulli condition. So here we essentially have something like, so it's an eigenvalue problem for the curl operator. And so we first solve this, and we study this problem by flattening the domain. And so using that, you can study the dependence of U on the surface eta, etc. So under the conditions I showed you on the previous slide, one can solve this problem. So, so one of the conditions was actually to make sure that we don't get multiple solutions for fixed values of this. Okay. Okay, and then after that, we also study the dimension of the kernel. And so, this is something you always have to do and which people usually skip. But here we use the geometric argument to show that essentially, so if you fix, so now I actually fix K and think of this as an equation for C. And if you do that, it turns out that this is the equation for a hyperbola. And so it turns out, so what we want is to get 2 different solutions. So solutions for 2 different Ks. We want the same C for 2 different Ks. And so to do that, we actually need to study the intersection of different hyperbolas. So there's a very nice geometric interpretation of that. And that also gives a nice geometric interpretation of the transversality conditions, which always comes into play in these bifurcation type of arguments. So essentially, it tells you that you need a transverse intersection of these hyperbolas. Okay, so once we have done that reduction to the surface, then we use Lyapunov-Schmidt reduction and the Kranov-Rabinovich type arguments. So at these specific values of C star, satisfying the, or specific values of C, where we have this nice transverse intersection, the kernel is two-dimensional. And so now I've reduced to the surface, so it's spanned by these cosine modes, if we assume the evenness condition. And so then Lyapunov-Schmidt allows us to reduce to a sort of algebraic system like this. And so the transversality condition essentially tells us that the determinant of these coefficients is non-zero. And so then you can solve these equations for C. Okay, so here, well, I didn't explain what T is, but so essentially what you do, this is the sort of the decomposition into elements in the kernel plus an orthogonal component. So T1 and T2 are essentially the amplitudes of these modes. Okay, and then solving, so so you get sort of trivial solutions if you take T1 and T2 equal to 0, but canceling those factors gives rise then to non-trivial doubly periodic waves. Okay, so that was a brief outline. Let me tell you something about open problems. Well, one thing which I think one should look into, and we're planning to do, is a variational bifurcation theory, much like Craig and Nichols. So in fact, there are two different variational formulations of this problem, one by myself and Lucaro, and an alternative one by Groves and Horn. And so I wanted to say something about their formulation because it's related to the work done by Walter Craig. So it turns out that there is sort of a very nice generalization of the Craig and Sulen formulation in the steady case. So it looks like this. So it's not so easy to see immediately, and I'll refer to the paper for more details. But here you can think of this operator K as a sort of generalized Dirichlet-Neumann operator. H is a generalized Dirichlet-Neumann operator, and then K is defined in terms of this operator. So this, in the irrotational case, when alpha is equal to 0, it reduces to what has been done by Craig and Sulen. Okay, so other questions which I would like to look at are higher dimensional kernels, combined with this variational theory, I think. Then a large amplitude is open, even in the irrotational case. And it would be very nice to look at the flow underneath the wave, especially in the large amplitude case. Can you get this chaotic behavior, which is known for Beltrami flows then? Okay, so those solitary waves and of course gravity waves are some other important open problems. Okay, so then I wanted to talk about another approach for constructing doubly periodic waves, which is inspired by a method from plasma confinement, in fact, so from magnetic hydrodynamics or magnetohydrostatics. So this is an idea from a paper by Lortz. So this paper is very nice, but it's in German, and I think for that reason it's not that well known. So his interest was in constructing magnetohydrostatic equilibria. So this is applications in plasma, in the design of nuclear fusion reactors, where you want to confine a plasma in a toroidal domain. And he was, he was in particular interested in the non-axisymmetric case, so corresponding to stellarator reactors. So his idea was to, instead of having axisymmetry, assume discrete reflection symmetry. And so using that method, he was able to construct solutions. And we'll do something similar here. So we look for solutions with these symmetries, which, essentially they are the same as in the irrotational case. So we have symmetry, reflection symmetry now both in the x direction and in the y direction. And we look for solutions which are periodic in x and y. Okay, so we assume in addition that U1 is bounded from below. So with these symmetry conditions, the streamlines are periodic. So that's not true in general. Even if the velocity field is periodic, the streamlines need not be. Okay, and then following Lorentz, we make this ansatz, so this is sort of true in general whenever you have a divergence-free field. It can always, at least locally, be written as the cross product of two gradients. And we make this ansatz globally, where h is the Bernoulli function. And then this function tau has, it has to satisfy this relation. And we take tau to be 0 at x equals 0. And with that normalization, it has an interpretation as the time it takes to travel from the plane where x is equal to 0 to a point P in the fluid, following a streamline. Okay, so let's look a little bit at the properties of this function tau. So it's periodic in the y direction, and it's not quite periodic in x, but almost. So if you move one period in the x direction, then what happens is that tau will increase by q, where q is a periodic function. And in order for omega to be periodic, it turns out that this condition is necessary. So the gradient of q has to be parallel to the gradient of h. So then it's natural to make the same ansatz as Lorentz, namely to assume that h and q are functionally dependent. And for technical reasons, I will assume that h is equal to beta times h, where h is a given function and beta is small. I mean, this is not really required. I mean, essentially what we'll need is some smallness condition on h, but I'm being a bit sloppy here. I don't want to specify exactly what you need, so I'll just assume that h is a given smooth function and that beta be small. Okay, so with this formulation, with this ansatz, we get this formulation of the problem, which looks a little bit like what we had in the Beltrami case, but now on the right-hand side here is not alpha times u anymore, it's some complicated expression. Okay, so here q and tau are defined as above, so actually they depend on eta as well. I forgot to change this. Okay, so one also needs to add an integral condition, and so an important difference compared to the Beltrami case is that the right-hand side over here is a first order operator in U, whereas it was 0th order before. And this is a huge difference. So I mean, this is not a sort of small perturbation of this in terms of regularities. It has the same regularity as the left-hand side. Okay, and then another observation is that any constant flow, uniform flow, is a solution for any h and beta. So we'll use these flows to bifurcate. Okay, so the main result then, so this is joint work in progress with Douglas and Christopher. So we assume that h is a given smooth function and beta is sufficiently small. And we assume that the wave vector k satisfies the irrotational dispersion relation, and that there are no other solutions except for reflections of this. Then there exists a family of doubly periodic solutions of this form. And U is rotational at order epsilon squared. So I think I'm running out of time, so I think I'll skip the technical details and just say that, so the basic idea is the same, that we first solve sort of the interior equations and then reduce to an equation on the boundary. But this is much more complicated compared to the Beltrami case because of what I said before about the regularity properties of this term. So following Lorentz, what we actually do is to use, well, we use Banach's fixed point theorem, which you can do if beta is sufficiently small. And so the important property is this. So you can use Banach's fixed point theorem to get a solution. However, this solution is not Fréchet differentiable with respect to the surface. So this is related to the fact that the function tau solves the hyperbolic equation. And when you differentiate with respect, essentially when you differentiate with respect to u in this hyperbolic equation, you lose derivatives. So you have Fréchet differentiability if you're willing to sacrifice some derivatives. Okay, and so then we plug this into the Bernoulli equation. And so we solve that using a version of Crandall-Rabinowitz, but where we have to sort of take this loss of derivatives into account. And essentially what we do is we sort of combine, so we combine a version of, well, when we solve the sort of range part of that, we combine the irrotational good properties, sort of the standard implicit function theorem argument in Crandall, in Lyapunov-Schmidt with Banach's fixed point theorem. And then we plug that into the other part of Lyapunov-Schmidt, and so then we have a problem with losing derivatives, but it's actually okay there because the problem is finite dimensional. And then an additional challenge is that the solution is, well, to prove that the solution actually has non-zero vorticity, that turns out to be a little bit difficult, unexpectedly. So the solution is actually not rotational at order epsilon. You have to go to the second order. Okay, so I think I will then, I've run over time, so I will definitely stop there.